The concept of impulse is really something that we've already looked at before, but just kind of expressed in a slightly different way. It starts out with Newton's second law of motion, which says F equals ma. But we know that acceleration is defined as change in velocity with respect to time. So substituting that in here, we find that F is equal to m times delta v over delta t, change in velocity over change in time. Well, to find what impulse is, how impulse is defined, we're going to multiply both sides by delta t. And that gives us this equation. Impulse, which is F delta t, the product of a force times the time that force acts, is equal to m delta v. Now really, we're going to define impulse a slightly different way. We're going to say F delta t is equal to delta mv, allowing the possibility that mass might also change during some kind of an event. So this equation here usually is going to be m delta v, because most of the time mass can't change. But if it can, we have to take into consideration that F delta t is equal to the change in momentum. So impulse, that's what this is. Impulse is change in momentum. For a system where it's not possible for mass to change, and there are a lot of situations like this, we can write the impulse equation this way, leaving out the possibility that m might ever change and just dealing with changes in velocity only. Well, here's an example problem. We're going to take a look at several different questions using the same situation of a 35 kilogram person jumping from a ladder that's 3.2 meters from the ground. Question is, first of all, how fast is she moving as she hits the ground? Here's our person. Again, the person's going to be a blob. We know that this person has a mass of 35 kilograms. Person's going to fall to the ground and be accelerated by gravity, we assume, and it's 3.2 meters to the ground. So our first initial question is, how fast is the person moving when they get to the ground? Well, final velocity in all accelerated situations is going to be square root of initial velocity squared plus 2 times acceleration times distance. If this person begins to fall from rest, we assume that's true because we don't have any other information, then initial velocity is 0. So final velocity is just the square root of 2 times gravitational acceleration, because that's what's acting here as they fall, times the distance. Plugging in numbers, that's 2 times 9.80 meters per square second times the distance of 3.2 meters. When we take the square root of meters squared per second squared, we'll get units of meters per second, good velocity units, and the number that we get here is 7.92 meters per second. Well, here's our next question being asked here. Same person jumping from the ladder, and now the question is, what is the impulse on her legs? Question being asked is, what is the impulse on her legs? Well, impulse is F delta t. That's impulse. That's what we're trying to find. But F delta t is defined as delta mv. Now, this is not a situation where mass is going to change. This person's mass isn't going to change as they hit the ground, unless something breaks off of them. We're going to assume that's not going to happen. So F delta t is going to be m delta v. Probably an easier way to express this. Well, the change in momentum is what impulse is. How does the velocity change? Well, this person hits the ground doing 7.92 meters per second. At some point, they come to a stop. That means their velocity goes to 0. So final velocity is 0. Initial velocity during the stopping is the 7.92 meters per second. So what's their change in velocity? Well, delta v is going to be 0, the final velocity, minus 7.92 meters per second, the initial velocity. So delta v here is negative 7.92 meters per second. It's got to be negative here because we have defined downward as positive. And to make the person stop, there's got to be some force, some acceleration going upward. So to find impulse, we just plug the numbers in here. The mass of the person was 35.0 kilograms. The change in velocity is negative 7.92 meters per second. When we multiply this together, we're going to get units of kilogram meters per second. Those are impulse units. It's going to be negative, and the number we get is 279. Negative 279 kilogram meters per second is the impulse. Next question here we're asking is, what is the force on her legs if the time of interaction with the ground is 0.055 seconds? So she's interacting with the ground. It's going to take 0.055 seconds for her to come to a stop. We want to know what force is on her legs. Well, impulse, defined as F delta T, we have now found is negative 279 kilogram meters per second. To find force, we would have to take that impulse, negative 279 kilogram meters per second, and divide it by delta T, which is 0.055 seconds. This is going to give us newtons, kilogram meters per second squared, as it should because it's a force, and the numerical answer is 5,072 newtons. So that's how much force. But it's negative, which means the force is in the upward direction because we earlier defined down as positive. Well, there is such a thing as angular momentum, and we're going to approach angular momentum by just looking at parallels. Like we saw parallels for linear motion and rotary motion. Linear and angular momentum also have some parallels. So we can say the sum of all momenta before equals the sum of all momenta afterwards in linear terms. Well, the analogy is very similar. The sum of all angular momentum, capital L is angular momenta, the abbreviation for it. Initially, that would have to be equal to, finally, the sum of all angular momentum. And what is momentum? Well, if momentum linearly is mv, then that means the parallel of m, which is I, moment of inertia, times the parallel of velocity, which is omega, must make up angular momentum. And there's also an impulse parallel, too. For linear systems, F delta T is equal to delta mv. Well, by the same token, then, torque times delta T must be equal to delta I omega. So, impulse for rotary, momentum for rotary, conservation of momentum for rotary motion. Here's an example problem for us to figure out. There's a weight on a rod spinning around the center at a radius of 5 centimeters. So this rod has a weight sticking on it at 5 centimeters and it's making a loop here. Has an angular velocity that's given to us. The weight slides out, so it's going to end up in a new position here, doing a new loop, and we want to know how does the velocity change. Let's draw a picture of this and set this system up. Here's the before. Over here is going to be the after. Initially, I got this rod. We're going to assume the rod is massless because we don't have any information about it. We've got a mass here. It doesn't say what that mass really is, but we do know that it's spinning around a 5 centimeter radius initially, and we also know that initially omega is 11 per second. After, well, the mass has slid farther out on the rod. It's still the same mass, whatever that is, m. Its radius is now 10 centimeters, and it's doing this bigger loop, which we would assume would be a lazier loop. Let's find out. That's our job, to find out what is omega. So let's call this final omega, as opposed to the 11 per second being initial omega. Well, conservation of angular momentum tells us this. The sum of the initial angular momenta equals the sum of the final angular momenta. Well, there's no really summing to do here because there's only one object. So let's just define this in terms of what angular momentum really is. So that means I initial times omega initial is equal to I final times omega final. Now I, for a weight on a massless rod, we learned in the last bunch of notes here, is just mr squared. That's what I really is. Well, let's substitute I equals mr squared in for this initial I and this final I in the conservation of angular momentum equation. So that means m times r initial squared times omega initial is initial angular momentum. We're assuming that mass doesn't change here, just changing positions, not its size. So afterwards, it's m times r final squared times omega final. And here's why it didn't matter that we don't know mass, because mass just drops out of this equation. So we get this new equation that says initial radius squared times initial angular velocity is equal to the final radius squared times the final angular velocity. We're looking for final angular velocity, so we'll solve this equation for that. WF is initial radius squared times initial angular velocity divided by final radius squared. So it's 5 centimeters squared, that was the initial radius, 11 per second was the initial angular velocity, and 10 centimeters squared is the square of the final radius. So square centimeters are going to drop right out of here, and we're going to get angular velocity units per seconds. If you take 5 and square it, multiply by 11, divide by 10 squared, you come up with 2.75 radians per second. And that makes sense that if the weight is farther out there, it's going to rotate more slowly.